2 of holographic phases.
Great. So yesterday we talked about Rice-Nordstrom mainly. So today I want to talk about charged matter in the bulk. So remember I said last time that there were two possibilities for the electric flux that we wanted at the boundary. That could either come from a horizon or from some charged matter in the bulk. So this morning at least we're going to talk about when the electric flux is coming from some charge density in the bulk. Okay, so when does that happen? Okay, so we can imagine having some action, so there'll be some Lagrangian for the bulk fields that will have, it'll be Einstein, cosmological constant, Maxwell, and then there'll be some fields that might be bosons or fermions that are going to be charged under this under the Maxwell field. And the general question you'd like to ask is, when do you expect the charge to be carried by these fields, and when do you expect it to come from a black hole? Okay, so the essential physical effect is about screening versus anti-screening. Okay, so at least in many situations, the essential physics has to do with screening, in particular electromagnetic screening, versus gravitational anti-screening. All right, so you do know this already. So screening is just the fact that if you have an electric field that's created by some charges that are fixed, and then if we add a positive and a negative charge to the system, then the positive charge will get other way. The positive charge will get pushed that way, the negative charge will go that way, and they'll try to reduce the field that, they try to screen, the pairs of charges will try to screen the electric field. Okay, but gravity doesn't work like that. If we have a bunch of mass here, and there's some gravitational field going this way, and then we add some more masses to the system, they both fall into the gravitational field, and the field gets bigger. Okay, so of course that's why you get clumping and structure formation, and that's why we're all here. Okay, so gravity anti-screens, and electromagnetic charges screen the fields. Okay. Right, so masses clump. Masses clump, but charges screen. Okay. So now what we want to do is take the charged black holes we were talking about last time. We had a horizon with flux coming out of it. And now, so let's say we've got some charged quanta floating around. Again, they might be bosons or fermions. And these charged quanta could get pair produced because of this electric field. So we imagine having a negative and a positive charge. And then the gravity and the electromagnetism want to do different things. Okay, gravity wants to pull both of these masses into the black hole. Okay, but electromagnetism wants to push the positive mass away and pull the negative mass in. Okay, and because we're in ADS, there's sort of a box, sort of reflective boundary condition at infinity. So this, if a charge gets pushed away, it doesn't radiate off to infinity, but will sort of end up sloshing around in the bulk. So the question of whether pair production, which just will certainly be happening, okay, because there's an electric field, the question of whether pair production discharges the black hole has to do with whether anti-screening wins, with whether gravity wins and they both fall into the black hole, or whether the electromagnetic screening wins. And then the negative one will fall into the black hole, the positive one will get pushed out, and the black hole will discharge, and you'll start getting some charged matter accumulating outside the black hole. Okay. So, right. So, does the black hole discharge? And so that depends on gravity or electromagnetism wins. Okay. So the simplest place to ask this question is at zero temperature. So for extremal black holes, okay. So right, let's see. So what are these forces, right? So for very schematically, so for gravity, the force is something like, it's going to depend on the mass. Okay, this is schematic. It's going to be the mass of the black hole times the mass of the particle times Newton's constant, whilst for electromagnetism, it's going to be the Maxwell coupling times the charge of the black hole times the charge of the particle. Okay, because that's the sort of the forces, the relative strength of the forces with respect to things are being pulled or pushed away. Right. Okay, so this is the particle mass. And I'm thinking of this as sort of the black hole mass. Okay. So the simplest place to ask this question is for an extremal black hole. So zero temperature. Then in some suitable sense, which let's say the charge of the black hole is sort of the same as its mass. And right, and that just means to compare the forces, we just basically have to compare the mass of the particle versus the charge of the particle. Okay, so in an extremal black hole, these are sort extremal planar black hole in ADS. Roughly, we can expect the charge to be expelled if the charge of the particle in units of the Maxwell coupling. Right, so remember the action is really R has a 1 over kappa squared in front of it, and the Maxwell term has a 1 over E squared in front of it, okay? That's what E and kappa are. So, good. So the charge will be expelled basically if the electromagnetic force will win if the charge of the particle is sort of bigger than its mass, okay? Okay, and so then we can expect heuristically that we're going to go to a phase where the charge is outside the black hole if the particles are relatively, at zero temperature, if the particles are relatively light. So this ties in a little bit with this conjecture of Al-Kani-Hamid et al. About gravity as the weakest force. And their conjecture is roughly that there should always exist a particle such that extremal black holes can discharge. Okay. Although they were thinking about flat space, not ADS. Okay, so let's suppose that we do have a light enough charged field in the bulk. So this is not an exact. So I'm using a particle, picture, a point particle picture. But I mean, in practice, if the fields have masses of all of the ADS radius, then one should really solve a wave equation, not just look at particles. And these equations can get shifted by order 1 numbers. But essentially, that's the important thing. Okay, so in essence, this is the criterion. Good. Okay, so how do you see this? So for bosons, you just start filling up. You start populating these boson states outside the black hole, and so because bosons can sort of all go into the same state, you see a classical instability. Okay, so all the quanta populate some coherent state. It's really basically Bose-Einstein condensation, yes.
Not a Coulomb crystal or something.
Not a what, sorry?
Not a Coulomb crystal. I mean, these.
Oh, good. Yeah. Right. So, nobody. Good. So, I tell you, let me talk about fermions for a second, and then come back to that. So, good. And so when you have fermions. So fermions are not like bosons. They can't all populate the ground state, and so they can't build up a coherent state. So you don't. So there's no classical description in this case. So in particular, you don't see a classical instability. Okay. And what you get is instead a quantum mechanical populating of the Fermi sea in the bulk. Right. So what's really happened? So what's happening in both of these cases is that you've chosen the wrong vacuum. Okay. So what's happening here is for the fermions, it's saying that the correct vacuum in the presence of this electromagnetic field and potential is to have a Fermi sea that's filled up to some point. But what you've done is taken the black hole with no Fermi sea, so you've just pulled out all the electrons, and this sort of quantum mechanical instability is just the Fermi sea wants to fill up again. Okay, so you want to populate the Fermi sea. So actually, back to your question. So what the question was is that bosons can do two things in condensed matter physics. They either, if you want to have a density of bosons, they either Bose condense or they can form a sort of crystal-like structure, right? Which I think has not been really thought about holographically at all.
Stefano Bolognesi and I wrote a paper about monopole crystals, which is the S-dual of this.
Is it? Yeah. So is it the same? Is that the same thing as what you talk about? But normally this kind of quantum mechanical, right? These crystals. I mean, they're not really classical.
Right, but in the S-dual it's classical monopole soliton motion.
Okay. So talk to David. Yes.
During the process that bosons come out, during superradiance, the area of the event horizon increases. The black hole.
So this is.
Does something happen in fermions also? Well, I mean, does the entropy of the black hole increase?
So okay. So it's often more convenient to think of this sort of in equilibrium. So fix the temperature, not the energy, and then you just, as I'll get to in a second, you lower the temperature, and then the horizon can decrease as a function of temperature, right? Right. So yeah, the real-time process. Yeah, it should be the same for.
I meant in the microcanonical ensemble. Does it?
Yeah, no, I understand. Yeah, it should be the same for bosons and fermions. I think. Yeah. Good. Okay. So right. So if you have some charged matter, if it's light enough relative to its charge, you can expect that the black hole wants to discharge into these charged fields. At zero temperature, Now, if you heat up the black hole, then what you're basically doing is you're increasing the mass of the black hole relative to its charge. And so eventually, so that's moving away from extremality. So eventually, gravity wins. And all the charges fall into the black hole. So for T bigger than some critical Tc, the black hole will be stable. Good. So one is led to a picture where above some critical temperature you have the black hole, and below some critical temperature there's a, so this would be a sort of fractionalized phase. And then below the critical temperature you have these mesonic phases. And often if you go all the way to zero temperature, all of the it doesn't always happen, but all of the charge can leave the black hole. And so you're left with a picture where the charge is carried by either a bosonic or a fermionic density of matter outside the black hole. So that what can happen, often there's still a horizon, or at least a sort of singular remnant of a horizon. So there can still be a throat. In fact, often there's a Lifshitz throat in the IR. So the geometry is not gapped. It can be, so in fact the geometry can be deconfined. But the charges are outside the black hole. Okay, so that's why it's like the quarks bind into mesons, but the gluons don't bind into glue balls because there's still a horizon. Yes.
So if you can make this picture in terms of some kind of phase transition between these two states, to what extent can you follow the charge degrees of freedom which fall into the black hole? Because these charge degrees of freedom, they have explicit surfaces which you can see, whereas in the fractional phase you can't see the Fermi surfaces.
I'm getting. We'll get there. We'll get there. No, that's right. So these things outside, and whether they're outside or behind the horizon, they look very different. They do very different things, and you can't.
Between the two, you should sort of maybe be able to follow.
No, I mean you can't follow them. 1 minute they're there, and then the next minute they're not. Or, I mean, gradually, of course, but.
In any case, when you mentioned the Fermi surface only is a sharp concept only at zero temperature. So at finite temperature, you can't use it to decide the equation of
That's also
the
true.
position of a phase transition.
Right.
And there could be other reasons for a phase transition, but that's not one of them.
Okay, so right. So maybe first I want to talk. Right. So these bosons, these states you get are called holographic superconductors. And for fermions, well, I don't know. I like to call them electron stars. And so, but these are really the same physical processes underlying the two cases. Just that one is bosonic and the other one is fermionic. And so this one, because you have a coherent phase of a boson that's condensed, this one will break the U1 symmetry, the global U1 symmetry spontaneously, and this one doesn't. Okay. So I want to very quickly say some things about the bosonic case, but mainly I want to talk about the fermions. So let's do the bosons. So in practice, what do you do? So in practice, you've got some action that looks like that. Okay, that's Einstein, Maxwell, and then some charge fields, maybe with the potential, maybe many charge fields. There are many things. So, I mean, what you do, so you look for a new solution for T less than Tc. There'll be a sort of hairy black hole where this phi this charge scalar field will not be zero. It'll have some radial profile, and then there'll be the gauge field as before, AT of R dt, and then some metric, which you make an ansatz of this form, f of R dt squared, g of R dr squared, dx squared, dy squared over R squared. Okay. So in above TC, we knew the solution was this extreme horizon Nordstrom, or maybe if we have some dilitons, it'll be a different normal state. But there often we know the black hole analytically. Typically, below TC, you can't, right, so you plug this ansatz into Einstein's equations, and you'll get some coupled ODEs for the charge scalar, the electrostatic potential, and the components of the metric. And normally you can't solve those ODEs. But people are now, these days, people now even solving PDEs, and as George Santos said yesterday, an ODE is almost analytic, so anyone can do numerics on an ODE. It's very easy. So you get a system of ODEs that you can solve numerically if you want to. And so what you'll find is that there will be, for t less than tc, there will exist solutions with phi not 0, but where phi, right, so the phi of r is a function of r, the boundary is at r equals 0, so maybe this is 1 over r if you want. This is the horizon at r plus, and you get some profile for the scalar field. And what you need to impose is that you want this breaking of the symmetry, you'd like it to be spontaneous, so you don't want to have an expectation value for the scalar field. So a source for the scalar field. So phi needs to be normalizable. So there'll be r to some power that will depend on the mass of the scalar field, and the coefficient of this fall-off by the usual ADS-CFT dictionary is the expectation value for the field. So just remember last time we were always saying fields in ADS-CFT had a sort of growing mode, and that's the source, and then the normalizable mode gave the expectation value. And so what we're looking for these spontaneous symmetry breaking is that there's an expectation value without a source. And what you'll find is this only is possible for t below tc.
Excuse me?
Yes.
I didn't get. Are you expecting that in time you'll see the transition from t less than tc to t to greater than tc, or this is beyond your?
No, in time you mean
As the system evolves, or that is beyond your approximation?
no. Okay, to check. So I'm looking at the canonical ensemble. So I'm looking at equilibrium as a function of temperature. You can also look at real-time evolution.
But so knowing that this is unstable, that eventually instead the real dynamics will make matter fall into the black hole, or did I misunderstand your first argument?
No, that's correct. But the time evolution can be a little tricky. Okay, so I don't want to. I'm happy to talk about it later. But let's just think. For these purposes, I think it's easier. So in fact, I can draw. Let me just do what I was about to do. So, I mean, you can make plots of, for example, the verb as a function of temperature, and you'll see it go to 0 when Tc is 1 and things like that. I don't want to. Let me not say anything about time dependence. No, I mean, I think if you start with it sort of super cooled, so if you're sort of in the wrong phase and you start with it, the black hole well below TC, then yeah, I think there will just be a time evolution, and the stationary state will be these superconductors. Yeah, that must be. And people might. I think there are some papers doing this.
Murata has a paper.
Murata. Okay. Yeah. There are papers. Yeah, I guess then you have to look at some 1+1 differential equations. Yeah. Okay, and then you can also easily compute. So once you have the solution, you need to check that it's the favored solution. So you should calculate the free energy and plot that as a function of temperature. And so the free energy you get by taking the solution. I erased. So the free energy is basically the on-shell action of the solution, which you have to renormalize. So that's a whole discussion that I don't want to get into now. And so you'll find that the Rice-Nordstrom black hole has some free energy as a function of temperature that maybe looks something like that. And then at TC, the new solutions appear, and they'll have a lower free energy. Okay, so this would be this curve is Rice-Nordstrom ADS. It doesn't have to be Rice-Nordstrom, whatever the normal state is, and this is the superconducting state. Okay.
Excuse me.
Yes.
Do you ever have a configuration where the black hole discharges completely and you only have, some hair or condensator?
Yeah, that's what often happens at zero temperature.
Okay, so this line, when you take it to zero temperature, you just mean that there's some condensate and no horizon.
Yeah, that's right. That's yeah. Sorry, no charge horizon. So the different things. So yeah, often there is a. Okay, in most of the examples, there is a horizon at zero temperature, but it's neutral.
There
Sorry?
should be temperature if there's a horizon, right?
Sorry?
Unless it's extreme.
No, well, horizon, it's a null singularity. But the right, okay. The geometry is not, the theory is not gapped, so it is still in a sort of deconfined phase.
I mean, there's an infinite proper distance in the book to get to.
That I'm not sure about, actually. It could easily be checked, but I don't do it. No, I think. Okay, I'm not. Yeah. No, maybe you're right. It's a null. Well, yeah. Okay, it's a null. So the Penrose diagram normally looks like that. Okay, it's a null. Normally it's a null singularity. Of a nice kind, in the sense that you can heat it up, an arbitrarily small temperature will resolve the singularity. Okay, so before moving on to fermions, let me just say two things. So again, I think the right question is what does this buy you, or what is this good for? So you can start doing lots of things. There was an interesting paper this morning about finite size effects that I haven't read yet. So I think the zeroth order lesson might be that it gives you a way of thinking about superconductivity in a system, in a strongly coupled system without particles, without quasi-particles. So, okay. So the UV, there's a UV and an IR picture. So the UV picture, which means from the point of view of the ADS4 at the boundary, okay? So the mass and the charge of this scalar field in the bulk translate into the scaling dimension and the charge of some operator O in your relativistic UV field theory. And the claim is that, yeah, so basically a charged operator O in the boundary CFT will condense when you place the theory at finite chemical potential if the scaling dimension of the operator is sufficiently small relative to its charge. Okay, so you take n equals 4 or whatever your favorite theory is. You say, I want to put it at finite chemical potential, as long as it has a gravity dual, of course. You put it at chemical potential. Will it become superconducting? All you need to do is just look at the list, look at the spectrum of operators, look at their scaling dimensions and their charges, and if there exist operators whose dimension is relatively small compared to its charge, then that operator will condense. Okay. And a rather intriguing thought that I haven't really been able to make precise would be this weak gravity conjecture might be dual to the statement that all CFTs always have such an operator, okay, which would then become the condensed matter statement that all CFTs become superconducting at finite chemical potential, or something like that. And that would be fun. Okay, so that's the UV picture, but which I think this is nice because it's a criterion for superconductivity that only depends on quantities that are manifestly well behaved, that are manifestly well defined for a quantum field theory. It doesn't depend on any, for example. Well, okay, no, that's just true. All right.
What's the difficulty with making that more precise?
Well, firstly, this weak gravity conjecture is not the most solid thing that's ever been proposed. It's in flat space. It's not totally clear what its generalization to ADS is. And there are various, well, we can, yeah. Also, that you can get confused about the normalization of charge, how you're meant to compare charges in different. Okay, yeah. I don't know. It deserves some thought, some more thought. Okay, that's all. But actually, perhaps also an alternative picture is the IR picture, and that's a question of. So this was a criterion for instability that I just gave, that was given in terms of UV data, okay? But often the normal state has some emergent, well, let's say ADS2 cross R2, or maybe it's Lifshitz, or maybe it's these, someone needs to find a good name for these things. They'll get lots of citations if they do, no doubt. So a generalized Lifshitz, or whatever it's called, with these hyperscaling violation exponents, okay? So all of whatever there's often in the normal state, there's some emergent scaling geometry in the IR, okay? And so these operators that had some scaling dimension delta in the UV will have a new scaling dimension in delta tilde, let's say, or delta IR, relative to this emergent scaling in the IR, okay? And often, well, a sufficient but not necessary condition for instability is that delta IR is complex, which is basically the statement that the effective mass in the IR is below the BF bound, the Bretland-Friedman bound for this scaling geometry. So the effective mass squared is below a generalized Bretland-Friedman bound. In the IR. Okay. Yes.
Suppose we consider compactification of string theory, in which the gauge field, the Maxwell gauge field, comes from the compactification of some Ramond field. Okay. In such a situation, you would have no light states that are charged under this gauge field. Mm-hmm. Wouldn't this be a counterexample to the claim that?
I don't. Yeah, I didn't make that claim.
I'm not saying you made it, but you.
So actually, yeah. Okay, very good. So people have tried, not in this weak gravity context, but in this context, to try to make stable. Okay, so there was this big question about the entropy density radius 2 cross R2, and maybe you always expect it to be unstable. And people, actually, so Klebanov and Pufu and Chris Herzog, tried to find, doing exactly what you said, trying to construct some examples where there were where there might not be any obvious instabilities. And I think they didn't totally manage, actually. I think they might, so there can also be brains that want to fly out of the black hole that are heavy but have a big charge. It's not always easy. Yeah, I think there might have been some brains that were charged, but I don't remember.
So what is the intuition why an electric force cannot be stronger than a gravitational force?
So what was the intuition?
Like the weak gravity, why?
Okay, I don't want to, let me see. So they have 3 arguments in the paper. One is that extremal black holes should decay, because if they don't, they might run in loops and have funny effects. The second one was that they hadn't found any string theory compactification that this wasn't true for. And the third one was that, for a reason I don't totally remember, they wanted monopoles never to be black holes. Okay, so if you write down a Twift monopole, is that Twift monopole? Yeah. Then its size is specified by the W boson mass, and then they wanted the size to be bigger than the Schwarzschild radius of the monopole with the same mass. And you know, if they had a good argument, they wouldn't need 3, right? It's anyway.
Also, no global symmetries in the theory of gravity.
Yeah, that's somehow related to these extremal black holes, perhaps being able to decay. I don't know what the status. It's definitely an interesting idea, and it might have interesting this actually is what's interesting, if it can be made precise, is that there would be a very concrete condensed matter analog of that would have nothing to do with quantum gravity. That would just be a field. I mean, it'd be very nice to have a field theory statement of what that means. Okay, so now let me just talk a little bit about fermions. Okay, sorry, so I think maybe they got lost. So there are 2 again, the instability has this IR criterion, but actually it's sort of even more dramatic in the UV, it's even more dramatic in the IR. So if you have an emergent theory in the IR with a bunch of operators, right, if one of the operators has a complex scaling dimension, then it wants to condense. Okay. Good. Okay, so fermions are sort of annoying and a bit difficult. So fermions are sort of intrinsically quantum mechanical. And difficult to back react. Should you wish to back react them. And so in principle what you have to do is it starts populating the Fermi C. All of these fermions that are populating the Fermi C have their own wave function. So you have to add together all the wave functions, calculate the expectation value of the energy momentum tensor on those wave functions, and then back react the whole thing. Some brave people have not been afraid to try to do that recently. So Subir and recently McGreevy et al. have started to look at the actual full quantum mechanical back reaction problem. It's not easy, but it's not impossible, it seems, either. But I'm not going to do that. So qualitative features. Qualitative features can be seen in a fluid limit. Okay, which has various names. So in a condensed matter context, this is called the Thomas Fermi limit, Thomas Fermi approximation. Where Thomas and Fermi, I think we're trying to describe the self-consistent wave functions of big atoms, okay, where you need to include the effect of each electron on all the other electrons. And then, so the electromagnetic side of this fluid approximation is called Thomas Fermi, and in gravity it's called the Oppenheimer-Volkoff approximation in gravity, which they use to describe neutron stars. And I guess in mathematics it's just called the WKB approximation. Okay. So let me describe what that limit is. And so again, this is primarily something that we're doing not necessarily because we want to, but because it's going to make the description a lot easier. And we just want to get a sense of what happens. Although it does have its own charm, and we are surrounded by fluids, so maybe there's a role, a natural role for fluids in an ADS-CFT context. Okay. So what do we need to do to get into this fluid limit? So, well, one thing we need is that the Compton wavelength of the particles should be much smaller than the ADS curvature scale. Okay, so the mass needs to be big in so short wavelengths. Okay. And then the other thing we need is if we want to get a star, good. So something that's a bit strange about what we're doing relative to astrophysics is that these are sort of planar stars, okay? And right, so it turns out that for planar stars, the degeneracy pressure. Okay, so how normal stars work, because gravity wants them to collapse, and the degeneracy pressure, the exclusion principle keeps them apart. These are going to be charged stars, so there's also an electromagnetic force that's preventing the gravitational collapse. And in fact, when you take the planar limit, it's really the electromagnetic force that's doing all the work. So the degeneracy pressure, so in the planar limit, it's electromagnetism, I think, not degeneracy pressure. That keeps the star from collapsing. And so what we're going to need if we want the star to exist is that these forces should roughly balance. So Km should be of order EQ. Now, in fact,
There are neutral versions.
not in the planar limit. So indeed, people in Amsterdam have looked at just neutron stars in ADS, which you can charge, but you can't. If you want to take the planar limit, you have to, which I'm going to get. You have to take a certain limit. And in fact, this is really the only thing that's well defined. So from now on, I'm just going to set Q to 1. Okay, which is going to be just the charge of the fermions. So there are some preferred units. So let's say the charge is going to be quantized in some units, and let's take 1 to be the quantum of charge. Okay, but we can still tune E, the electromagnetic potential coupling. Okay, good. I mean, in fact, for a solution to exist, we need, as I said, we need Km to be a little bit smaller than E, but they're of the same order. They're of the same order. Okay. Okay. So this was we need that to balance the forces. I mean, there can be factors of 100 or 10 or 1/10 in this equation. I'm just saying that they scale. If you want to start it as some people, well, as it's sometimes a good idea, if you want to start putting factors of n in, I'm just saying these two guys have to scale in the same way. Okay. All right, so now that's actually enough to get a fluid description. And so you can show that in this, when you take these limits, the Dirac equation and the corresponding expectation values of T mu nu and J mu, this is in the bulk now, right? The charge and the energy in the fluid can be described by an ideal fluid. And actually in the 60s, some guys actually just did this explicitly. You take the, we're going to see more carefully in a minute why this is a WKB limit, but you basically take your Dirac equation in some fixed background, and you write down the WKB wave functions, and you sum up all the WKB wave functions, and you can actually show that the T mu nu, these expectation values you get, are those of an ideal fluid in the space-time.
You did this in flat space or in
They did it in flat space, yeah. Yeah, and the paper is a little bit, old-fashioned. It might be nice for it to be done, just to derive these fluids from first principles in ADS.
Someone could probably do it quickly, right? With this current law.
Maybe, I mean, you have to do some maybe. Okay, so an ideal fluid has just a T mu nu, which is the energy density and the pressure. And so, for example, so the whole point of going to this ideal fluid is that it's a local description. Okay, you have just at each point, the fluid thinks it's living in flat space. So at this T mu nu, the rho, for example, the energy density is just the integral from m to a local chemical potential, which I'll tell you what that is doing in a second, of the energy times the density of states times the energy, right? So, and for example, if you have a Dirac, just a free Dirac equation, the density of states would be, if I got it right, something like this. And so, right, so remember, because they have a mass, this is just the Fermi C, right? This is just the energy. You're taking the states in the Fermi C you're populating the states up to mu local. The minimal state has energy m, because you need to put in the rest mass energy of the fermion to start populating anything. So this integral is from m up to the chemical potential, and you're just summing the energy of these states, okay? And that gives you the energy of the fluid. Okay, so what's mu local? So mu local is the chemical potential seen by the fermions at a given point in the space-time. And what is it? Well, the chemical potential is the same as, it's just the electrostatic potential, so that'd be AT at that point. But then what you have to do is redshift into the rest frame of the fermions that are sitting at that point. And so the local chemical potential is AT, it's just the Maxwell potential, but then you divide it by root GTT. R. Okay. So these Fermi surfaces have a local chemical potential that they see, which is this redshifted chemical potential. So there's the proper chemical potential or something like that. And so because you're dealing with an ideal fluid, there is actually, so I should say, this is the redshift. like. Okay.
You know, I'm not sure you know this, but it's just like Tolman's law of the temperature, right? I mean,
Yes, 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 of course, yes.
So it's natural that chemical potential is the same.
Yes, that's right. Yes, yes, absolutely. But good. But if you don't like these expressions that are coming out of nowhere, you can actually get the fluid equations of motion together with all of this stuff falling into place. They're actually from an action, because I'm only dealing with ideal fluids. And actually there are many forms of the action, but a particular simple one is this thing called the Schutz, or Schutz, whatever, no, form of the action, which we generalize to charged fluids, where L, the action of the Lagrangian of the fluid, is just, in fact, the pressure of the fluid as a function of, let's say, at least at zero, let's be at 0 temperatures per second, of mu local. Okay, that's an action. So pressure there's some formula for the pressure that would be analogous to the density. Okay. So if you vary, and this makes sense, by the way, in terms of, if you think of thermodynamics, right, that the on-shell action is like the free energy, and in the fixed chemical potential ensemble, the free energy is the same, is minus the pressure. Okay, so it's not surprising that the action is just the pressure. Okay, so similarly to the superconductors, so actually it's even easier. It's a bit easier because for the superconductors we had phi, a, t, g, and f, the metric functions, and now we don't have phi, and the fluids don't have additional equations of motion. They're just dragged along. So at each point, the density of fluid, so for example, the T mu nu, the density of the fluid, is just fixed by some fixed integral in terms of mu local, and mu local only depends on the metric and on the Maxwell field. So the fluid degrees of freedom are not independent. They're dragged along. They're fixed by the background. So you have so you get some ODEs again, and you solve them for the metric and the Maxwell potential. Of course, you solve consistently, including the back reaction of the fluid, and that will tell you, you'll get some profile for the pressure, the energy density, and the charge density of the fluid. And what you find at 0 temperature, let's say, is so R. Okay, because we're at extremality, R goes to infinity in the IR, which may have been what Julian was saying a second ago. And then the boundaries at R equals 0, and then the pressure and the density of the fluid will just go to 0 at some radius, and that's the boundary of the star. Okay. Good. So I want to say 3 things about this setup. Any questions? Okay, so three comments. So there are many things you can start similar with the superconductors. Once you have solutions and you can start building them, then you can start probing their phenomenology and seeing if they're good for anything. But I'm going to rather make some sort of conceptual, more general comments. So the first one is related to something Shiraz mentioned yesterday. So so you just find these solutions. I think they're honest, back-reacted star-like solutions to GR with a negative cosmological constant. So the IR geometry, so you find this back reaction at 0 temperature, and then you look at what the metric looks like here. And so the IR geometry is often Lifshitz, or is Lifshitz, in fact. if you don't have any dilitons, it's just Lifshitz. And so probably somebody else wrote down the metric, but if not, this is the Lifshitz metric. And so the point is that time and space scale differently. Okay, there's a z, the dynamical critical exponent here. And the way we think about, so the normal state, in this simplest model I'm talking about at the moment, the normal state, or whatever, the black hole had z equals infinity, which is the ADS2 cross R2 near horizon geometry of extremal horizon Nordstrom. And so roughly what's happened is that the reason this ADS2 exists is sort of the flux coming through the extremal black hole horizon that's sort of pushing the space-time open and allowing this infinite throat to exist. Because of these charges that are now populating the IR, the flux gets eaten up. And actually by the time you get to the far infrared, there's no flux left, and so the geometry sort of collapsed in some sense. So this finite z, we can sort of think of as a partial collapse of the ADS2 throat. But now we can ask, so what is z? Okay, so z is fixed. Z, right, just make the ansatz, you can find the scaling solution. So z is fixed by E kappa, and the mass of the field in ADS units. And so let's say this is an order 1, sorry, is big, is a big quantity. So you find that z is order 1 if E squared, the Maxwell coupling, goes like kappa over L. Okay. So I didn't use this relation up to this point, but you just write down the solution. So this is okay. This is what you find, and so what this is telling you is that basically that the Maxwell coupling. Sorry, the gravity coupling is the square of the Maxwell coupling, okay? Which actually is kind of amusing, right? It starts, you start thinking about D-branes, and string and open and closed string couplings, but I don't actually know any realization of this using D-branes. But okay, so you need this particular relationship between the Maxwell and the Newton couplings.
Could you translate that into N, please? What would the...
N is up to other people. But I think, so let me put it straight. If kappa is the same as E, so if you do N equals 4, I mean, I don't know whether, okay. Oh, kappa over L is, kappa is just L Planck. So this is like N to some power that you probably know. But yeah, the point what I'm getting at is that in many of the ADS-CFT examples that we understand the best, which doesn't necessarily mean that they're representative of or generic, but the best understood, the canonical ones, E is of order kappa. I mean, you just have a 1 over kappa squared outside the whole action, right? And then you have some R and S squared. So what happens in that case, so if E is of order kappa over L, L is just there to make the units work, you find that Z is very large. Okay? So for example, N equals 4 at large N or something.
So it's very near ADS2.
Exactly. So at any given radius, of course, right. So exactly. So it's a small change, but because the throat is infinite, by the time we get to the end of the throat, it makes a big difference. But it's a small, exactly. So
The finite energy considerations, it's identical to ADS2.
sorry, at what?
Finite energy processes.
Yeah, right. No, absolutely. But so, for example, but the entropy will go to 0. I mean, yeah, it depends what limit you want to take. That's right. So that's right. So locally, at any R, which is close to ADS2, close to R2. Okay. But the far IR, which is the sort of strict t goes to 0 limit, if you like, is qualitatively different in two ways. Well, one is that this entropy density goes to 0 as t goes to 0. But secondly, all the charge is outside the black hole, outside the horizon. So it's really a different phase of matter in that sense, even though metrically it's very close. So for me, the primary motivation for taking this limit is just to go to a regime of the solutions where you can have the effect that is there, just be there at order 1 rather than something in order. Yes?
The IR geometry is sensitive to the form of the density of states.
No. So although I should say, not the effect of the equation, the equation of state of this fluid has not been explored at all. But right, limit. Yeah. But if you have no dilaton, so if it's just Einstein-Maxwell charged fluid, then you can always look for a scaling solution, right, where the metric has this Lipschitz form, and in the scaling solution, right, so the IR is a scaling solution. I already wrote the metric, and the Maxwell field is some number over R to the Z. And then what you find is that P, rho, and the charge density are all constants. P0, rho 0, sigma 0. And so all the equation of state will change is how these constants are related to each other. So that will change things like Z. But it won't change the fact that it's Lipschitz. Was that a question? Yeah.
Excuse me. Yeah. So you call it a star, but just to be clear, there's still no mass gap, right? I mean, because it's a planar limit, so.
There in these, there's no. That's right. It's deconfined. There's no mass gap. Yeah. And not that confinement and mass gap are equivalent, but there's no. Yeah, there's no mass gap. So Tadashi, I mean, you can put these things in soliton geometries, and Takenagi and some other people have done that.
How does the chemical potential of these solutions compare with the chemical? I mean, how does it scale with N or kappa?
No. That you want to keep. So right. So the chemical potential is free. I mean, that's something you fix at the boundary, and so you can make you can make a phase diagram. So what you want to fix, right? So for example, of the free energy against T over mu, for example. Those are just well-defined things. And you can heat these things up. I won't say anything about it, but when you heat it up, what you get is a black hole with some charge. Then it's Weisse-Nordstrom for a bit, and then there's sort of a cloud of fermions, and then you go out to the boundary. Okay, so you can have mixed states. And so you'll just find it's very much like the superconductor case that there'll be Weisse-Nordstrom ADS for any T over mu that you want. And then at some point the the star will come in and have a lower free energy. So T over mu is just
Explain, but when it wins, what is the order of a mean? Let's
yeah,
say t equals 0.
that's right. So there will be, yeah, it's probably pretty small, I think. There will be powers. So yeah, I think it's probably a small number. And, yeah.
In both these cases, the bosonic and the fermionic, this condensate or not condensate, whatever this fermionic thing outside, is it localized away from the horizon or does it extend?
No, not at 0 temperature. It's
Yeah,
it's like that.
Yeah.
Okay, it's not. Although, of course, when you're looking at the density, there's a factor of r squared. Or so. Okay, anyway, the energy density as a function of r looks like that.
Yeah.
When you heat it up, it gets pushed away from the horizon, and you get a sort of cloud sitting outside the horizon. You can also, when you add dilitons, it can also have the consequence of pushing the guys away from the horizon. Is that a question?
So isn't it right that in order to get a solution that at finite distance significantly deviates from ADS2, you have to work in a parameter regime that we have no examples of in a field?
I think that's correct. Yeah. But I would also say that the world we live in is in a parameter regime that we don't have a factorification of either. So, but yeah, no, absolutely. So that's. It would be very nice to have obviously UV examples in this parameter regime. Obviously.
You can cook them up quite easily. You just need some small internal cycle, and you wrap a D-brain around it.
But it's sort of, it has to be kind of parametric. I mean,
Joe and Eva have examples of.
Yeah. No, that's I you know, my philosophy. I think landscape's a big place, and I don't see why it wouldn't be possible. But just to be clear, I think the main reason to do this is just to push this effect, this qualitative effect that I know is there, into an order 1 regime so that we can just study it more easily. Okay, that's the main purpose. And as
the neutron star in the flat background, if he grows too big, then you will collapse into the black hole.
Well, okay, so good. That's what this T over mu is. So it's a bit good. Okay, I'm doing okay. So right. So where's the remnant of this Oppenheimer-Volkov bound? Okay, so Oppenheimer, that's the critical. So the neutron star has this critical temperature, right? And so these guys in Amsterdam that I mentioned, you go to global ADS, okay, where you're on a sphere. Okay, the answer to your question is yes and no. Okay, so that's why I'm taking a step back. So you take your global ADS on a sphere, and say you put a neutral fluid in the sphere inside ADS. Okay, then you can have a star in ADS that's literally a neutron star, just the same as in astrophysics, but in ADS. Okay, that guy has a maximal radius. Okay, and if you try to put in a number density that's too big, it will collapse, and you get a first order transition from a star to a black hole. Okay, now, and so you can never take the planar limit of this neutral guy because it always collapses before you get the planar limit. Is the large black hole? It's a large star limit in ADS. Okay, right. When the radius of the star is much bigger than the ADS radius, that's the planar limit. But now, if you charge it, if you make the fermions charged, and you take the right scaling limit, you can get to a planar limit. Okay, where right. Okay, but there, once you've got to the planar limit, you lose a scale. Okay, so the planar limit. So the reason you can have a first order transition in global ADS is that there are two scales. There's T, the temperature, and then there's the radius of the sphere. Okay, in the planar limit, you lose this radius of the sphere, right. What am I trying to say? I'm sorry. You want to be at 0 temp. Sorry, you have there's a radius of the sphere, and the transition happens when the mass is of order the inverse radius of the sphere at 0 temperature. Okay. Now in this planar limit, you lose this radius. Okay. So so you don't have a scale for the transition to happen at. But when you heat it up, then you do have a scale. Okay. So let me say that differently. In planar ADS, you have a neutron star that goes up to some radius, But this radius doesn't mean anything. All radii are the same, okay, because it's just planar ADS, and you can scale it. You can scale it around. Now, when you heat it up, that's not true anymore. Okay. So what happens? So anyway, so this star, this planar star, doesn't have an Oppenheimer-Volkoff bound, okay, because there's only one of them. There's only one scale. When you heat it up, indeed, so what happens is that you start getting. Actually, it's better to think of cooling it down. So start with Weiss and Nordstrom at some high temperature, that's stable, and as you cool it down, at some critical temperature, there'll be a special radius where the charged fermion can exist, and its forces will balance exactly at a specific temperature. And you keep cooling it down, you get a band where fluid can exist. And as you keep cooling it down even more, this band extends all the way into the infrared and eventually eats up all the charge. And so it turns out that this transition is much smoother than it would have been in this. So it's first order in this. The Oppenheimer-Volkoff transition is first order. And this guy here actually turns out to be third order. Okay. So there's a third order phase transition when these things appear. So this third order transition is the analog of the star collapsing. But it doesn't really look like a collapse, but it's the analog. So if you heat it up, eventually the black hole wins, and the stuff wants to fall into the black hole. All right. Yes.
Suppose you had a black brain, an ordinary black brain, in a regime where it was unstable, less favorable than one of these guys. Would you be able to see the instability of this black brain somehow?
Sure, not classically, but quantum mechanically, yes.
What calculation would you do to see that?
Okay, I'll go that right now. Well, okay, I'm sort of more or less going to go there in a second. So how might it? Where will it show up? So that was one, right? So yeah, no, right. So I mean, what you'll find is if you calculate the density of the charge density of the fermion. So
you say the Hawking cloud around it would basically backreact so much that it would destabilize.
Right, and good. Yes. So what you find is there is a density there which you just didn't include if you're in the right vacuum.
And because the charge is so large, it's actually classic.
Yes, exactly. That's right. Yeah, exactly. Like tables, and I mean, well, the density is large. Right. So you calculate the VEV of like psi. You know.
So the determinant is not subdominant, basically.
That's right. When mu is large enough, yes.
But why doesn't that happen with usual Hawking radiation also? Why fermion?
No, that's down. That's down by factors of n.
You don't scale the charge with.
Yeah, you have to. That's right. Yeah. I mean, you can do there's a loop, and you can just calculate the density. And so, but what I wanted to say, where this shows up, is so if you ever solve the Dirac equation in a star, in a geometry, in a black hole, in a geometry, and find a pole at finite k, okay, which is otherwise known as a Fermi surface, okay, which people have been doing recently. So you just calculate in the boundary the 2-point function of some fermion operator. It's a function of omega and k, and if you find a Fermi surface pole, it can be a non-Fermi liquid. It doesn't matter. That's telling you that there is a density of states in the bulk, because when you see the Fermi surface, what you're seeing is the excitation of the highest guy, right, out. And of course, this Fermi surface is only there because it's filled up, all right? and there are states in the Fermi surface, and those states back react, right? And you don't have the option. I mean, the back reaction might be parametrically small, but it's there, right? So Fermi surfaces, right, imply a Fermi C, and the Fermi C has an energy and a charge, and that back reacts in the solution, okay? And that qualitatively changes the infrared of the IR geometry of the solution, okay? Even if it's very small, it has a qualitatively big consequence, yeah.
I thought when you do these two-point function calculations, the Fermi surface is in the boundary, not in the bulk.
Sure. So that's correct. But basically there is a Fermi surface in the bulk too. It's the same. So the thing. Yeah. I mean, so there are some. Basically, there's some states. So if you decompose these guys into sort of momentum states of the field, these correspond to particular wave functions in the bulk that are also filled. So in fact, you can prove. So this I was just saying a moment ago. You can. There's, I think it's called the Migdal relation in condensed matter physics, and that also holds in curved spacetimes. Okay, so you can get the charge density, which is something like psi dagger psi. Okay, it's just okay. I'll get it wrong, but it's related to the existence of these poles. Okay, so and in fact there's there are various steps of people proving this, but the final version that I think is very nice is so Hong Liu and Iqbal have just a general proof that whenever you have singularities in these Fermi, let me say it differently. This fermion two-point function, you measured at the boundary, but you didn't have to go all the way to the boundary. You could have sat here and just measured some fermion two-point function. And the only difference is that you're in a curved space, but you still have to. These guys prove that you fill up the states, and there's a density of charge. Okay. Yeah.
So I didn't quite understand this at this point. If you see a Fermi surface, you're saying there is a Fermi C.
Yes, in the bulk.
And the next statement is that it's hard to see, or that you've missed it and you have to take the back reaction into it.
You missed it, and it has a back reaction. Yeah.
Now, so your infrared geometry is necessarily incorrect if you haven't taken.
Okay, that's a slightly stronger statement. I think there are generically, yes, there are cases where the fermion wave functions are not localized in the far IR, and then you're okay. But you have to use alternate quantization and various things. So there's some big window. So in these MIT papers, there's some big window of masses and charges of the scalar fields, and there's some small little region down here where I think the Fermi surfaces are not really in the ADS2. They're outside the ADS2, and those ones don't back react. But if they're supported in the ADS2, then yes.
If you're working in the usual parameter regime, then you would have to go to temperatures that are parametrically small in order for this to be possible.
So so the framework of these lectures is not so much the phenomenology of these states, but the conceptual question of what are the phases of matter that you get holographically. And the question there is whether the charge is at zero temperature, whether the charge is inside or outside the black hole.
But if you're distinguishing zero temperature from temperature 1 by n, that's a bit, that's a bit academic in the large n limit.
So I think this has very much the flavor of the information loss paradox, actually, where late times don't commute with classical limits. And here it's indeed the zero temperature doesn't commute with the classical limit. And this is very much related to the entropy of the Ricci-neutron black hole. So I think it is a conceptually important question. And what I'm showing here is that you can push that question into a classical regime where you can trust it, which is not, people that grew up eating n equals 4 for breakfast don't like this parameter regime. When that makes sense, and I would definitely like to have a UV embedding of all this. But it's more, I'm trying to find a model where you can address conceptual questions in a controlled way. Okay. Yeah. Okay. So last comment. Right. Okay. But I agree, and I think the reason for this is it's harder, it costs more energy to put, because fermions don't all go to the ground state like bosons, For a fixed charge, it costs you more energy to put the fermions in because they have to stack up these Fermi seeds. And I think that's what's really behind this difference. And there is a difference between bosons and fermions. Okay, let me just, so that is true. Because, for example, one conceptual question is that one lesson in condensed matter theory, as far as I understand, is that the Fermi liquid is a very robust state of matter. And really what's happening here is that this exotic thing that you try to set up really wants to become Fermi liquid-like as far as the charge carriers are concerned in the low temperature limit. And so if you want to, well, okay, I mean, large N will help you, but yeah. All right, sorry. So let me just actually say some things about the Dirac equation in these stars. Right. Good. So I told you this was a WKB regime, and in fact, so you can actually find. Okay, so there's some Dirac equation that I took a fluid limit of, but now let's go back to the Dirac equation, and what one looks for, and see what the wave functions look like. So psi, the wave function, is going to. It turns out you can write it as e to the I s, and then the thing that goes here is EL over kappa. Okay, and this limit I'm working in, EL over kappa in this limit. Actually, maybe I don't even need to go. Sorry, I don't need to go to that limit. This thing is big. Yeah, sorry, in that limit. And so, when you can write the wave functions like that, and this parameter is big, this is a WKB wave function. Okay, and so, right, so what can you do? So you take this Dirac equation. The Dirac equation has, just take a two-component, I mean, it doesn't really matter. So psi satisfies the Dirac equation. You can get a Klein-Gordon-like equation by sort of, squaring the Dirac equation. So it satisfies the Klein-Gordon-like equation in the bulk. And that Klein-Gordon equation you can put in a Schrodinger-like form. Oh, sorry. Okay, what am I trying to do? I'd like to show you all the poles of all these Fermi surfaces. Okay, so this star is many, many Fermi surfaces at different radii. Okay, because it's locally a fluid of fermions. So I want to show you that explicitly. And so to do that, I write down the Dirac equation, and you can massage it. Right, so I want to look at the zero energy Dirac equation, because I'm going to look for the poles, okay, the KFs. I want to see the Fermi surfaces. So in this, I want to set omega to 0, and then I want to see where all the poles are in momentum space. The Dirac equation with omega equals 0 can be written in the Schrodinger form, where there's some potential that's R. There's some potential that depends on R. Psi of R equals 0. Equals 0 because you're at 0 energy, right? And what does this Schrodinger potential look like? So we're nearly done. So V, one finds, this is off the horizon, that's the boundary. Looks a bit like that, okay?
It's different for left-handed and right-handed fermions, right?
Yes, that's correct.
But the poles are there for both?
Right, yes, this so certain, yeah, no, that's right. Actually, Chris Herzog wrote a paper about this a week ago, and I haven't digested it yet. But there is some issue with the helicities. Yeah. Okay. So, right, and so then, but this potential depends on K, and we're looking to find the pole. The poles show up as bound states of the potential. And so what happens is that if K is too big, when K is big, there are no zero energy bound states. And then when you lower K, this potential moves down And so for some intermediate values of k, you get some bound states. Okay, and then when k is 0, the potential looks like this. Okay, so let me just explain to you what that means in terms of Fermi surfaces. That means that so I'm looking at 0 frequency. I'm looking at the 2-point function of the fermion at 0 omega as a function of k. And so, right, and the WKB wave function, remember, is moving very quickly, okay? So the WKB wave function is sort of bouncing back and forth between these two sides. And where the WKB wave function is localized is at the turning points, okay? Because it's moving really quickly. The only place that it spends any time is when it turns around and comes back. So WKB wave functions are localized at the turning point, right? So if I plot the wave function in the WKB limit, it's going to be some big peak here and another big peak there. Okay, that's what the WKB wave function looks like. All right. And so these poles, right, exactly, so this is k. So above some k, there are no poles, and then there's going to be basically a whole bunch of poles at different values of k that correspond to the bound states that you get as you move this potential up and down with k. Okay, and what these are what you're seeing are all the different Fermi surfaces in the bulk at different radii. And so, for example, this, right? So the lowest one is localized at the end of the star, and also the far interior of the star, and that makes sense because the density is going to 0 at the boundary of the star. I lost the plot. At the boundary of the star, the density is going to 0. So here, the Fermi energy the Fermi momentum is going to 0. Okay. So to excite a fermion at the boundary of the star, you don't need much momentum. You need zero momentum. So the boundary of the star is where there's a 0 momentum Fermi surface, and also in the far interior because it gets redshifted. So the Fermi momentum also goes to 0. Okay, and then anyway, the picture is you have many Fermi surfaces at different radii corresponding to the different radii of the star. And then what you can do, as I suspect Subir mentioned in his talk, is you can take the volumes. So you can find, using the WKB approximation, you can find, although what I'm about to say is also true beyond WKB, but in a WKB approximation you can just analytically find all of these KFs, and then you can add the volumes of all the Fermi surfaces. Okay, so all these n Fermi surfaces, and you'll find that they add up to the total charge. Okay, and this is this Luttinger relation. Okay, and what that's telling you is that these electron star geometries are viewed as a state of matter. I mean, they have an interesting phenomenology, but viewed as a state of matter, they're essentially Fermi liquids. Okay, you have a bunch of Fermi surfaces, and the volumes of these Fermi surfaces add up to the total charge. Okay, there's no. By the way, you can have more general cases where there's a horizon here, plus fermions outside, and then there'll be a missing Luttinger count. Okay, so the volumes won't add up to the total charge. They'll add up to the total charge minus the flux from the black hole. Good. So let me just repeat that because this is where we'll start this afternoon. Is that both the holographic superconductors and the electron stars, when all of the charge is carried by stuff outside the black hole, it looks like a phase of matter that would be essentially recognizable in essence to condensed matter physics. Okay, so in one case you have Fermi surfaces whose volumes add up to the total charge, so you know where everything is. It's all in these Fermi surfaces. In the holographic superconductor case, you broke the symmetry, and you're going to have a Goldstone boson. Okay, which is so the low energy physics would just be this Goldstone boson, which is also what you expect to get in a symmetry broken phase for bosons. So the low energy physics, in essence, is conventional. Okay, even though the phenomenology is not. sort of as a conceptual phase of matter, there's nothing exotic about them. So the exotic guys, so what I'm going to do this afternoon, is go back to the black holes. Okay, so I think the charged black holes are really what has the potential to be dual to exotic phases of matter, sort of in principle, not just that they have interesting specific heats or whatever, but that as the different phases of matter. Okay, I better stop. Sorry.
Any quick questions before we break for coffee? No, Sean will be around throughout the coffee break if you want to ask him something in private. Thanks, Sean, again.